Thanks everybody for coming on the last day of the conference here. I'm Dr. Tanya Harrison, and I like to call myself a professional Martian because I work on rocks and robots on the Red Planet for a living. I've spent over the last 10 years working in mission ops for a few different NASA Mars missions, including Opportunity and Curiosity, and then the Mars Reconnaissance Orbiter. And today we're going to kind of go through a little summary of what kind of things we have to deal with when we're designing technology for rovers or space missions in general, take a little tour of one of our rovers, take a look at some really pretty pictures from our rovers, and then how we actually operate some of them and the future of how that's going to look, and then what we're looking forward to for operating things on Mars right now. So when we talk about doing rover operations or designing things for rovers on Mars, the stuff that you tend to think of might not be as high-tech as you would expect. So my cell phone, for example, has, we'll fix that. That was not my cell phone, luckily. So my cell phone has a 64-bit 2.39 gigahertz processor with a 12 megapixel camera that can shoot 4K videos and display 3D and augmented reality content. It can download data at LTE speeds and tell me within a few meters where I am at any given point on the Earth's surface. And it can even tell me where I should eat dinner tonight. All of that is in a device that can fit in my pocket. But the latest and greatest Mars rover that NASA has right now has a 133 megahertz processor. Its science cameras are 2 megapixels, and we get data back from the rover at a speed that would make most people want to throw their laptop out the window in comparison. But why is that the case? It's because we have a lot of limitations that we have to deal with when we're designing things for space missions. Space is dark and cold, but also hot, and we'll kind of explain that in a little bit, and everything is really far away. And so this makes a space where, even though the universe is infinite, the workspace that we can work within is actually very confined. So we have to innovate inside a box when we're trying to think of what we can do with these space missions. So there are a lot of really big constraints that we deal with. One of them is latency, or basically how slow your signal is coming back and forth. The bandwidth issues between Earth and Mars or anywhere else in the solar system, high G-forces during launch and landing, power, and radiation. So latency is something that, unless we manage to discover subspace communication from Star Trek, we're never going to be able to get past that because we're just limited by physics. We're limited by the speed of light. So if you look at this animation, you can see a little tiny dot that is moving from Earth toward Mars. This is a real-time animation of sending a signal at the speed of light from Earth to Mars. And at its closest point, when it ever gets as close to Earth as it's going to be, the shortest amount of time that takes is a little over 3 minutes. Generally, it takes more between 10 to 40 minutes, depending on how far away Mars is at any given time. Today, right now, Mars is 228 million miles away, which comes out to a 20-minute one-way light time. So if we send a signal to the rover on Mars, it takes 20 minutes to get there, and then 20 minutes for that signal to come back. So obviously, that's not something that's really conducive to sitting there and driving a rover with a joystick, for example. So it's not actually how we do rover ops. You can see in the time that I gave that spiel, your signal still hasn't even made it to Mars. Bandwidth is another huge thing that limits us a lot. To give you some examples of the bandwidth and like the downlink rates that we get from different spacecraft that are out in the solar system right now, the Mars Reconnaissance Orbiter, or MRO, sends us back data ideally around 1.3 megabits per second. Mars Odyssey, which is much older, it's the oldest operational spacecraft in orbit of Mars. It's been there since 2001. We get data back from that at 30 kilobits per second, so it's like a 28.8 modem speed. And then Voyager 1, which is outside the solar system at this point, happily heading off into interstellar space, is 160 bytes per second. So we're just trickling data back from these things. And in comparison, I checked my average internet speed at home before I came here, and it's 13 megabits per second, so it's significantly faster than this. But we're limited because we don't have a lot of ground stations on Earth to actually get that data back. And there's huge competition to use those ground stations because there's only 3 for NASA around the world, and we share those with all of the other missions in what we call deep space, so anything that is beyond Earth orbit, essentially. And so there's a lot of competition for all of that space basically being used in the different radio frequencies. So it's really limiting how much data we can send back from a lot of these missions. High G-forces are a really big one, so I'm sure if any of you have ever seen a rocket launch, there is a lot of force going up, but then when we're landing something on Mars, particularly a rover, there's a lot of force coming down as well, particularly during the phase when our parachute gets deployed. And that's a huge shock because you're coming through like almost at terminal velocity, and then you stop immediately as this parachute comes out, and you're kind of gently coming down after that. So the highest G load experienced by Curiosity, for example, was not during launch, but it was actually during the landing sequence. It was 9 Gs at the point when the parachute detaches. So after this, I want to emphasize that everything you're going to see in this presentation is an actual photograph that has been taken by a spacecraft at or orbiting Mars. Some of them look like they could be CGI because they're so cool, but I really want to emphasize that they're not. And one of the neat things about the Curiosity rover is that we actually had a camera mounted on the belly of the rover called the Mars Descent Imager, or MARDI. And this camera took pictures as the rover was landing on Mars. It's the first time we've ever done this. And we were able to put those together into a really cool movie that I think is one of the best products that NASA has ever released. So what you're going to see are the actual images taken by the Descent Imager. And then behind it, we've overlaid the audio from Mission Control at the Jet Propulsion Laboratory, or JPL, in Pasadena as the landing was happening. So this video is 2.5 minutes long.
Thrusters have been re-enabled. We will control our attitude on shoot. We are decelerating.
So that's the heat shield separation.
Decelerating and descending. We are at 150 meters per second.
Dynamics phase. Come back again with wrist mode dynamics.
Wrist mode is nominal.
We are 9 kilometers and descending.
Leads active. Valid range.
Net filter converged with a velocity correction of 0.7 meters a second.
We've acquired the ground with the radar.
An altitude of 8 kilometers.
Heat shield has separated. We've found the ground.
Expand tones due to earth occultation as expected.
We're standing by to prime the Emily engines in preparation for powered flight. We're down to 90 meters per second at an altitude of 6.5 kilometers and descending.
So you can see the view is kind of moving all over the place because they're coming down on the parachute, so the parachute is moving around.
Flight EDL, we've got some TWIDA warnings. It is in battle short mode, so it should power through them.
Director Earth Communications at this time. We may have lost it already. We're down to 86 meters per second at an altitude of 4 kilometers and descending. We've lost tones from Earth at this time. This is expected. We're continuing on Odyssey telemetry.
Ground solution equals minus 10.8 meters, vertical velocity of minus 82.8 meters per second.
Start enabled, standing by for backshell separation.
Signal to Odyssey is still strong.
We are in powered flight.
So here now it's stabilized a little bit, and this is where basically the retro rockets have kicked in, so it's coming down a little bit more stable than it was
about 70
before.
meters per second.
Signal to Odyssey remains
down to 50 meters per second. 500 meters in altitude. Standing by for sky crane.
Constant velocity accordion nominal. Altitude error 5.9 meters.
We found a nice flat place.
So that's actually the dust being kicked up by the rockets as the rover got closer to the surface.
Down to 10 meters per second. 40 meters altitude.
That's the wheel coming down as the rover was landing, because that was its landing gear,
Sky
as
crane
well as
started.
its wheels.
Descending at about 0.75 meters per second as expected. Expecting bridle cut shortly.
Signal to Odyssey remains strong.
Tango Delta nominal.
Yeah. UDLCOM configured.
Review stable.
UHF telemetry.
Review stable.
UHF is good.
Touchdown confirmed. We're safe on Mars.
Obviously, we made it. And Curiosity's been on Mars for 7 years now. I don't think any of us that worked on the mission outside of the engineering team thought that this crazy sky crane system was actually going to work. You basically had to come down underneath a parachute, and then at some point the parachute detaches, and the rover is coming down on a little sky crane system, has to figure out where it's going to land, lower the rover from the crane, then the crane has to detach and fly away and crash somewhere else so it doesn't just crash down on top of your rover. And the engineers are explaining this to all of us, and we're just staring at them like they're crazy. And you're just like, whoever thought this would work? We're all going to lose our jobs on August 6th. Like, everybody's sitting there panicking, and it actually worked. So they did an amazing job, and we're going to use this system again on the next rover, which is launching next year, and we'll talk about that rover a little bit later. This whole descent sequence was 622 separate images that were all stitched together. So power is something that I think we really take for granted here on Earth. In your house or your apartment, there's probably dozens of power outlets. I'm sure a lot of you have power packs in your backpack right now for your phones, and your phone has a battery that can maybe last a day or more, depending on how much you use it. But in space, power is more precious than gold. Every single watt that you can get counts for something. We don't have a lot of power because you're limited by things like mass, you're limited by how much sunlight you have in places, and you're limited by complexity and the cost of the mission, which is another huge limiting factor that we won't really talk about today because that's its own talk. But to give you an idea of how little power we're dealing with when you're trying to power these things, the Opportunity rover, which we lost contact with last year and called end of mission for this year on Mars, was powered on an average a day of 80 watts through its solar panels. So that's less than it takes to light up a light bulb in your living room. And we're managing to drive around and do science on that little amount of power. But the trade-off for that is that the speed is very, very slow because it takes a lot of power to drive something. So the top speed of Opportunity and its twin rover, Spirit, which we lost contact with back in 2010, is only 0.11 miles per hour. Curiosity, on the other hand, is a much larger rover, which we'll see soon. It runs off of a nuclear battery instead of solar panels, and it gets 110 watts from that nuclear battery. Generally speaking, depends on how much it needs, if it's doing science or if it's driving, but sort of the nominal background level is around 110 watts. But it's even slower because it's so big. The top speed is 0.09 miles per hour. That number might not mean anything to you, so to give you kind of a reference frame, an average human walking speed is 3 miles per hour. And to compare it to something else that's in space, the SpaceX Tesla Starman heading out toward Mars has 20,000 watts per hour in its electric battery with a top speed of 155 miles an hour. Radiation is another really big thing that we have to contend with. This is a graph kind of showing you things like the US annual average radiation exposure. I'd like you to note that this is a log scale, so these are huge differences between each of the columns here. You'll notice that the 180-day transit time to Mars is more than the Department of Energy's recommendation for the limit for a radiation worker. And then spending 500 days on Mars, which is how long it takes you to get there, hang out on Mars until it gets back to a good point where you can launch back to Earth, is basically the same as that initial transit time to get there. So you're dealing with really high doses that we're not really sure how they're going to affect human health, but they also have really big effects on your electronic components as well. You can have a single hit from a stray cosmic ray or a solar energetic particle coming out of the sun, and it can kill your entire mission. We think that we've lost at least one Mars mission before because of an errant cosmic ray hit like that. So it's something that we have to take into account when we're designing what we call radiation-hardened electronics or rad-hardened electronics for these types of missions. So now we're going to take a little tour of our latest and greatest Mars rover with the help of some good technology. Do you have the HoloLens? Oh. So I couldn't actually bring the rover with me, unfortunately. I don't have that much power. But we figured this could be the closest cool thing that we could bring you. So this is Curiosity, shown to scale, and usually the first reaction from people is that rover is massive, and it is. We usually like to say it's the size of a minivan. So when it landed, it was all kind of tucked up like this, and the first thing that tends to get deployed after we landed is the mast. So it kind of wakes up and says, oh hey, I'm on Mars. So back here in this, basically the butt of the rover, this whole giant thing is the radioisotope thermoelectric generator, or RTG, and this is the nuclear battery for the rover. And you can see, since it's so large, it would have been really impractical to put solar panels on something this big. It would be heavy, it would be expensive, and it would just look plain ridiculous. It would look like it has these giant wings. So it was talked about for a little while and then deemed just completely impractical. So this battery runs off of the decay of a ceramic form of plutonium-238. There's 11 pounds of it in the back of this rover, and it generates about 110 watts per day, like I said. But the problem is that the rover actually draws more power than the battery can generate at any given time. So it charges itself up and stores power through a thermocouple, essentially. And then when the rover needs to draw energy from the battery, it can do different activities, but it limits us in terms of how much we can operate per day, because the rover has to spend a lot of time sleeping to recharge the battery. So you make a lot of trade-offs. Is this a day where you want to drive, or is this a day where you want to do science? Because you can't necessarily do both of those things in the same day, just from the amount of power that is required. Then we have this little antenna thing that's waving here. We have two different antennae on the rover. One of them we use to contact Earth directly, called the DTE, or direct to Earth antenna. We don't use this one very often because you can't transmit data back at a very high rate from it. But if there's some reason where we need to try to talk to the rover directly, we can. But generally we use a high gain antenna on the rover to contact the orbiters that are at Mars right now. So NASA has the Mars Reconnaissance Orbiter, the Mars Odyssey Orbiter, and the MAVEN spacecraft, which is a mission meant to study the atmosphere. Europe has their Mars Express mission and the ExoMars Trace Gas Orbiter. And then India has their own orbiter called the Mars Orbiter mission, which we don't really tend to use to communicate with any of these spacecraft, but if there was some kind of emergency, we probably could. Okay, can you trigger the wheels, Allie? So as I mentioned before, the rover moves incredibly slowly, and so we wanted to try to give you an idea of just how slow that process is. Let's see. Do you need me to trigger it from here? Okay. The rover's so big, it's hard to fit the whole thing on the stage. It also doesn't all fit in one frame in the HoloLens. So the rover has a suspension system called the rocker bogie system, which has a bunch of different pivots on it so that when the rover is moving, it tries to keep the main body of it as level as possible, even though the wheels underneath it might be doing something like this. So it can drive and steer with the four corner wheels. The middle wheels don't allow it to crab walk, so it can't drive sideways, but it can turn in place like you're seeing here. And this is about the top speed that the rover moves at in terms of driving back and forth. Then move the rover back. So all in all, when you look at the rover from this view, you can't see all of them, but it has a ton of different scientific instruments on them. There's 17 separate cameras, 11 separate science instruments, and over 30 separate motors that control everything from the wheels to the motion of the arm to the motion of the mast. So this is a really complicated piece of equipment. Oops. We fell asleep there for a second. There we go. So one of the cool features that we have on Curiosity is this robotic arm. And the arm is 7 feet long. And at the end of it, we have this turret that weighs 34 pounds. The entire arm is about 225 pounds. And the turret can rotate 360 degrees because it has a few different instruments on board. One of the instruments is a camera that is mounted at the end, and we'll talk about that a little bit more in a minute. It also has something called the alpha particle X-ray spectrometer, which was supplied by Canada. And without getting into the details of how it works, because it's pretty complicated, it basically tells us what the rocks are made out of on Mars. On the side closest to me over here, you can see a little bit that's crossing. That's actually a wire brush that we use to brush the dust off. And in true NASA fashion, we can't just call it a brush, it's called the dust removal tool, or the DRT. The rover also has on the very bottom of the turret in this configuration here, there's a drill that uses a commercial off-the-shelf drill bit that you could get at a place like Home Depot. And we use it to take little tiny core samples that are powdered, and then we can scoop it up with a scoop on the arm and dump it into sample analysis instrumentation that's on the deck of the rover. And again, that instrumentation is very complicated, and I won't get into how that works because honestly, I don't even understand how it works. I'm a camera person. But the cool thing is the camera that we have at the end of the arm for the rover, it's called MAHLI, the Mars Hand Lens Imager. And for the non-geologists in the room, which I'm guessing is most of you, hand lens is basically a little tiny like magnifying glass that we keep on hand to take really close-up looks of individual grains of sand or grains that are inside of rocks to take a look at the properties of them. So the main goal for the science for this camera is to take close-up views of the rocks that we're looking at on Mars. And we've had microscopic imagers on Spirit and Opportunity, but they were fixed focus cameras. So you just kind of had to hold them at a consistent distance away from what you were looking at, and you couldn't do anything other than that microscopic imaging. MAHLI, on the other hand, has a very close minimum focusing distance, but it can also focus to infinity. So we can take this 7-foot-long robotic arm, hold it straight up, and take panoramas as we look around with the rover. We haven't really had like a huge obstacle in front of us to have to do that versus just taking pictures with the cameras on the mast. But there is a cool feature that we can do with this particular camera. I think some of you know where this is going. So Curiosity is the first rover that we've sent that can actually take selfies on Mars. And it works the same way it would if you were taking a selfie with your cell phone. The rover holds the arm out, turns the camera back toward it, and takes a picture. But since the rover is so big, you can't fit the entire rover in a single frame, obviously. So what we have to do is move the arm in a way that we try to keep the optical axis fixed, and then the main body of the arm is all that is generally moving. You can see the whole thing is moving, but we try to keep it relatively consistent. And then you take about 50 to 70 separate images, stitch those all together, and then you get a really awesome view of the rover just sitting there on the surface of Mars. A lot of people ask how we do this because when you see these selfies, it looks like the rover is just sitting there. You can't see the arm held out. You don't even see the shadow from the arm in a lot of cases. Sometimes you can, but generally you can't. And that's because of the way that we're moving the arm is very intentional to keep the main part of it out of the field of view. And then when you stitch them all together, you do it in such a way that the arm kind of gets removed from view. But this is another one of the really cool products that we're able to release for the public from Curiosity, because it gives you a real sense of this thing is sitting on the surface of Mars. We built this thing as humans and it's there. And we can watch how it's changing over time. We can see dust that's collecting on the deck. We can see, unfortunately, damage that's happening to the wheels, and we'll talk about that in a little bit. And you can see some of the cool little things that get left behind as well. So, Ali, if you can zoom in on the Morse code in the wheels. So the engineers like to have fun on some of these missions, and one of the things that we have in the wheels are these marks here, and they spell out JPL in Morse code. So as the rover drives along on Mars, it leaves these tracks in the sand, and it just says JPL over and over again. Eventually, these tracks get erased by wind, so they won't be there forever, but it's kind of a fun thing. There's also little badges all over the place for the mission itself. There's an American flag. There's a NASA badge. Yeah, so we have these little badges like this. And unfortunately, so those holes in the wheels are intentional. We also have some holes in the wheels right now that were unintentional. If you've ever seen some of the pictures of the other landing sites we've been to with places like Viking or Spirit or Opportunity, they tend to be very flat places because of the landing mechanisms that we've used. We've had to be very conservative. Curiosity, because we had this sky crane system, allowed us to be a little bit more daring in where we actually landed the rover, and we had a mobility system that allowed us to drive a lot farther, theoretically speaking. When we got there in this place called Gale Crater, the rocks that we've been driving over ended up being much more rugged than anything we've ever experienced on the surface of Mars before. And so they've been really hard on the wheels, and unfortunately they've punctured some holes in them. Luckily, the holes are not anything that are inhibiting our ability to drive, but we do look at them with these selfies and with some close-up views with that MOLLE camera, kind of holding it down so we can see the wheels, to look at where the damage is. Is it in just the aluminum body part of the wheel? Is it damage to the actual grousers that are holding those bits together? Is there any damage to the titanium interior structure? And we've learned from this experience. So for the Mars 2020 rover, which is like Curiosity 2.0, we're actually going to make the wheels out of titanium instead of aluminum, so that they'll hopefully be a little bit more beefy to deal with this more rugged terrain. We also have some other main science cameras on Curiosity, on the mast up here. So there are a few different cameras. The big round thing at the top is the chemistry and camera, or ChemCam. And this is the instrument maybe some of you guys have heard about on the internet. It's famous for shooting lasers at rocks. And why would we do that? Well, we can shoot this particular laser at rocks, and it basically turns them into a plasma. And then we look at the light that is emitted from that plasma, and the rover can analyze it. Well, technically the humans back here on Earth analyze it. But the rover collects the data, sends it to us, and we look at that light, and from that we can look at the elemental composition of those rocks. And then from that, we can try to figure out how those rocks actually formed. And it tells us about the geologic history of the particular area of Mars that we're in, this crater called Gale Crater. Just underneath that, we've got two smaller cameras. You can see one has a bit of a smaller opening than the other one. These are the Mast Cameras, or Mast Cam. And one of them is a 34 millimeter wide angle camera. The other is a 100 millimeter zoom camera, or telephoto camera. These were originally meant to be two identical zoom cameras, and unfortunately they were de-scoped. NASA removed them from the mission due to delays in technical development, but we're going to get those cameras back on the 2020 rover, which should be really exciting. So these are our main science cameras, and the cool thing about them and MOLLE is that they're the first cameras we've ever sent to Mars with a bare pattern filter on the CCD. And for those of you that aren't familiar with what that means, that's the kind of sensor that's in your cell phone or your consumer digital camera. It has the RGB pixels that are meant to simulate what it would look like if you were staying there looking at the scenery around you as a human. Everything we've ever sent before has had filters that are ideal for science, but it's approximating things that are useful for us to learn about the rocks, but not necessarily what you would see if you were a human standing on the surface of Mars. So we get all these false color views where from the Viking missions in the 70s, Mars is very orange. The later missions, kind of in the 90s and early 2000s, we get a much more realistic color palette where Mars is more of a brownish color, but actually if you dust off that red-brown dust, it's actually gray underneath all of that. So it's a lie that Mars is the red planet. It's actually gray, kind of like the moon, underneath all that iron dust on the top. So this is giving us our first real views of what Mars would look like if you were standing on the surface as a human looking around you. The camera also has filter wheels, though, so we can do some more complicated science if we need different filters. And we're going to use that on future missions as well. So with that, we're going to switch back to the slides. So this is an example here of one of those selfies that I was talking about. And you can see some of the features that I mentioned before. So I apologize to this half of the room. Here's one of the holes in the wheels, the unintentional holes, not the intentional ones. You can see dust on the deck of the rover. So when we landed, it was nice and like bright white and shiny. And over time, dust has kind of settled out of the atmosphere, a little bit like snow. So it gets redder and dirtier over time. You can't see the arm in this view. You can't even see a shadow from it, just from the way that things were moving. There's the battery back there, one of the antennae. So it's really cool. We can keep a good eye on what the rover looks like over time and how it's dealing with the hazards of Mars. So now we're basically taking an epic road trip with these rovers on Mars. And so I went through with some of my colleagues that worked on Curiosity and Opportunity and asked them, what are your favorite pictures that you got to take of Mars with the rovers? Because yes, these are robotic missions, but at the end of the day, they're being operated by humans back here on Earth. And I really want to emphasize that. I think to this audience, that's obvious. To the general public, maybe not so much. So there is a very human side to a lot of these missions. Well, to all of these missions. So my favorite rover that we've ever sent to Mars is Sojourner. It's the thing that got me interested in Mars in the first place. It landed on Mars when I was 11 years old, and I thought it was absolutely amazing that we were able to take something, throw it at a planet 200 million miles away, and land it in a specific spot on that planet, and then tell it to drive up and analyze the rocks there. Even though I work on these missions now on a daily basis, it still blows my mind that we can do that. It's really incredible. It's hard even if you're trying to drive an RC car here on Earth to get it to do what you want it to do. So doing it here where we're writing lines of computer code, sending them off into the ether and hoping that the rover does what we want it to do, and I would say 90% of the time it actually does, is really incredible. So Pathfinder, the lander here, this was the Pathfinder mission. It landed on the surface of Mars, and it kind of unfolded like a little flower, and then Sojourner drove out of it, and it's a lot smaller than Curiosity. It's more like the size of a shoebox. And it drove around, and it leaves some little tracks on the surface here. But NASA released this composite GIF of the rover driving off of the platform from Pathfinder and onto the surface of Mars. This might not seem very impressive now because the resolution is really low and we see GIFs all the time, but in 1997 this was a huge deal, especially to an 11-year-old who thought that space was awesome. And so this video here is what made me want to work on Mars rovers. I knew I wanted to be involved in space because of this one GIF from NASA. This whole sequence here in real time took about 2 minutes, so this rover is similarly slow to the other ones. It's just sped up for convenience sake. This image was chosen by Mike Siebert, who was one of our flight leads on Spirit and Opportunity for 13 years. And this was a panorama that we took at a location called Cape Tribulation along the rim of Endeavour Crater, which was one of the main targets that we were driving through with the rover. We really wanted to investigate this crater to figure out how the area that Opportunity was in formed. The images taken through this panorama were taken back in 2015 on the 3,894th Martian day of operations for a rover that was only supposed to last for 90 Martian days on the surface. So it well outlived its warranty and kept taking amazing panoramas like this. And at the time that this was taken, this was the highest elevation that Opportunity had reached since it left the previous crater it was at, Victoria Crater. And when it got there, it held out its robotic arm. So this is kind of the turret for Opportunity. And it took an image where we could see this American flag that's on the arm. And this was put on the arm as a tribute to 9/11 because the folks that were working on the arm, Honeybee Robotics, they were in Lower Manhattan at the time. And so they went and they actually retrieved pieces of the World Trade Center and incorporated them into the rover. And so we have a memorial to 9/11 on Mars in the form of Spirit and Opportunity. This is a panorama called the Everest Panorama because it's the highest point that we've ever driven on Mars with any rover. And this was taken by Spirit back in 2005 by Ashley Stroop, who is another longtime member of the Mars Exploration Rover's mission. And she said when she took this, she didn't even think about the significance of the fact that it was also the first image to collect wheel tracks that were left on the surface of Mars by a woman. She was actually the first woman to command the rover to drive on the surface of Mars. And then she also got to take this image with the tracks captured in it. So that was a pretty amazing moment. The image was taken at about the same resolution as human eyesight to try and give a good idea of what it would look like if you were standing there. Even though it is a false color image because we weren't using those bare pattern filters, it still is a pretty good approximation of what it would look like to human eyes. And there's so many images in this panorama, it took about 3 days to image all of it. This is a view, again from 2005, from the Spirit rover, capturing dust devils moving around on the surface of Mars. So Mars is a really dynamic place, especially in terms of weather. And these little dust devils, they basically form when you have temperature disturbances in the atmosphere. So one layer is really warm and one layer is really cold, and it ends up picking up the dust off the surface and causes these tiny tornado-like things. If you've ever been, oh, we're in Las Vegas, you've probably seen some of these before. Or if you're from Arizona, where I live right now, we see these things all the time. If you're in some places where I give this talk, people have never seen a dust devil before, so it's a little trickier to explain. But these are actually really helpful things to us on Mars, because over time, as you saw with Curiosity, dust settles out of the atmosphere and collects on the rover. For Curiosity, that's not really a problem because it's powered by its nuclear battery. But for solar-powered rovers like Spirit and Opportunity, that's obviously not a good thing, because if you have dust that collects on top of your solar panels, that's going to cut down the amount of sun that's getting to the panel, and it's cutting down the amount of power that you're getting to your battery. But completely unexpectedly, these dust devils come by every once in a while and they clean off the solar panels, sometimes to the level where the power is almost as high as the beginning of the mission. And so these things have been very serendipitous for the Mars rovers that have been solar powered. Unfortunately, they were not serendipitous enough to save Opportunity, which we'll talk about in a couple slides, but they're pretty cool. And I love things like this that help demonstrate that Mars is an active place. There's stuff going on there right now. It's not just this dead rock that's floating around in space. One of the descriptions from the Apollo astronauts of the moon is that it is magnificent desolation, and I would say that applies to Mars very well. Also, this is the Rub' Khali dune field, and these are tracks looking back toward the north, because Opportunity spent a lot of time driving almost due south, going along to crater by crater as it was continuing on its mission, because the rover just wouldn't die, so they didn't investigate one crater till there was nothing else left to do, and they're like, well, we might as well just keep driving south to the next crater. And it managed to drive across these dunes. Unfortunately, it did get stuck at one point for more than a month, but it did manage to get out at one point and kept on driving. And the Arabic translation for these dunes is the empty quarter, which is very fitting for this particular image. Now, this is from orbit. This is not from one of the rovers, but I wanted to show you what these dunes look like from orbit. And this is actually a view from the Mars Express spacecraft, which is a European mission that is still orbiting around Mars today. And it captures these really stunning color images of Mars. So all of the dark stuff that's around the light area, these are all sand dunes that kind of look on the ground like the ones that we just saw in the previous image. This area here is the northern polar cap of Mars, which is made up mostly of water ice, so the kind of ice that you get out of your freezer, essentially. The south polar cap of Mars is actually made of carbon dioxide ice, or dry ice. And then this up here, some of this is frost, but these wispier areas, like up in the corner, those are actually water ice clouds that are hanging out over the edge of the polar cap. So again, it's a thing that kind of reminds us that weather on Mars is a really dynamic place. This is the last panorama that Opportunity ever caught before we lost contact with the rover. It's composed of 354 individual images taken from May 13th to June 10th of last year. So the last day that they were taken was Sol 5111 of this 90 Sol mission. Sol is a Martian day. The last day here, a few days beforehand, we had been hit by the strongest dust storm that we've ever seen on Mars, not just from the time that we've actually been there with spacecraft, but even from the time that we've been watching it through telescopes. And unfortunately, the storm started slightly north of Opportunity, traveled immediately, like right over the rover, and then quickly encompassed the entire planet, to the point where we couldn't even really see the surface from orbit. We lost contact with Opportunity pretty quickly, and then once the dust storm subsided, 4 months later, we were hoping that some of those dust devils would come by and clean off the solar panels, because we were reaching the time of the Martian year where we expected those dust cleaning events to happen. The nice thing about Mars, because it doesn't have oceans, is that the weather is incredibly predictable. We're really good at telling on sort of a week by week or bi-weekly basis what the weather is going to be like at any given time and any given place on Mars. We waited through dust clearing season, and unfortunately, we still weren't able to get contact with the rover. We tried a few different methods, like one where we waited for the rover to call us. It didn't work, so we tried one where we were like, hey, are you there? Please wake up. That didn't work either. And so in February of this year, we reached the end of that dust clearing season, and we had been in summertime for the rover, so it was nice and warm. And we were moving toward fall when temperatures would start to be a problem. So if the rover's survival heaters weren't kicking in, if they weren't running, the battery would discharge and we would expect the electronics to basically freeze up. And so NASA decided to declare end of mission. So this mission lasted about 15 years on Mars after it was only supposed to last for 90 days. So I would call that a resounding success, even though we lost it. And I would say that there was nothing, I'm almost gonna cry. There's nothing more fitting to have taken out this rover that couldn't die than the strongest dust storm that we've ever seen on Mars. And I'll sign off on the vacation photos part with this blue tinged sunset from the Spirit rover. So sunsets on Mars are actually blue, unlike the sunsets on Earth, because you have all of this red dust in the atmosphere. The color of the dust and the grain size of it is just the right size so that the light penetrates the atmosphere more efficiently, and so it spreads that blue light more. And then as you get farther away from it, the sky gets more orange. So even though it's a different color, it's still something that's very familiar. We can look at this and recognize that's a sunset, and it's something that connects us, I feel like, to Mars. And there's actually a motto on one of the calibration targets on one of the rovers that says 2 worlds, 1 sun, which I think is really beautiful. So now we're gonna try to do a demo of some more futuristic Mars technology using the Xbox controller that I dropped earlier, but seems to be working, so. There we go. Trying to do this on a separate screen is a little bit like teleoperations, which is kind of funny. So what we have here is a ClearPath Robotics rover that is actually in the Mars yard of the Canadian Space Agency. And yes, Canada has a space agency. It's near Montreal. And we use this area in Canada, I moved here from Canada, to test out different Mars rover tech. So we have a lot of rover bodies there that you can mount different technology on and test it here in this field to see how it's working out. You can also use it to test different mobility systems. But this here is a rover with some tech from a company called Mission Control Space Services. And they are working on technology that we can use to actually help rovers drive a little bit more intelligently and without so much of our help. So let's get this up. So one of the things that we had to deal with Curiosity, like I mentioned before, was the wheels getting a lot of damage from the rough terrain that we've been driving over. And so to try and mitigate that damage, the rover drivers started to move off of the rough terrain onto more sandy areas. But that caused its own problems. If you've ever tried to walk in sand on the beach, you know that it is not a graceful process. You tend to sink into it, you kind of fall around a little bit. And this rover weighs 2,000 pounds, so it of course sunk into the sand as well. It was sinking as much as 30% of the wheel diameter into the sand. And so there wasn't a happy medium. You're either getting a little bit stuck and hoping that you don't lose the rover. That's how we lost the Spirit rover actually, was that it got stuck in sand and we couldn't get it out. But you also don't want to keep damaging the wheels to the point that the rover doesn't drive anymore either. So MCSS is working on this technology where the rover can try to figure out for itself where the terrain is safe or not. And it's doing this using a combination of stereo imaging, where it can make terrain maps. So here it's doing an image classifier where it's distinguishing different types of terrain. So here the green stuff is vegetation, the brown area is sand, the red area is stuff that it's kind of ignoring because like on Mars we're not dealing with stuff like buildings or pavements, but we have to deal with it in the Mars yard. But it is also doing assessments of what it thinks the soil hazard conditions are. And it does this through a system called ASAS, the Autonomous Soil Assessment System. And so this works basically by collecting a bunch of data as the rover is driving. You have a training data set where the rover is constantly figuring out, okay, I'm driving over this terrain, it's safe, I'm not slipping very much, these are the properties like the grain size and what it looks like and what it feels like to the rover. And then it combines all of that together to try and figure out, okay, I know what this looks like, I know what this feels like to my wheels. So now I'm going to look at stereoscopic images that my cameras are taking and try to predictively figure out where areas might be safe or not to drive over. So I'm actually going to drive this rover in Montreal with an Xbox controller from here in Vegas. We don't do this for Mars, again, because of the time delay, but when we're actually on Mars as astronauts, we're going to be so confined to what we can do in terms of like how far you can go from the base because you don't have a lot of oxygen necessarily, or the power that you have for the rover that you could drive in as humans. You're going to want to do a lot of teleoperations for robots anyway, so it's a good exercise to practice operating these things remotely. So if we start moving around the Mars yard, you can see here I'm getting closer to this rock. And green means this is pretty safe, I think I'm okay, I can keep driving over this. But as we get closer to the rock, you can see yellow and red. So the rover is determining, I don't think I'm supposed to drive over that stuff. So it's really easy to figure that out geometrically if you're looking at something like, oh, that rock is too tall, I shouldn't drive over that, or that slope is too steep, I can't drive on that, because we know the steepest slopes and the biggest obstacles we can drive over, because we test for that here on Earth before we send the rovers, and then we tend to kind of cut that in half to be super safe. So even if the rover could drive over something 30 centimeters tall, you might say, well, we don't want to take any chances, so we're only going to drive over stuff 15 centimeters tall. But this is working non-geometrically. It's actually trying to figure out the properties of the material itself to tell you whether or not it's safe for the rover to be driving. So I don't want to drive over that rock, so let's try steering away from it and see what's over here. So it's almost like they designed the yard to be pretty safe for rovers to drive in, who would have guessed? But it's a good test bed for this type of technology. And the more they have these rovers driving over different types of terrain to build up these training data sets so the rover gets a better idea with its mobility systems, okay, these wheels can drive over this stuff but not this stuff. This other mobility system can maybe handle certain terrains better than others. You can try to feed these into future rovers. And then ideally, it's a system that you would build into a rover on Mars or anywhere else, and as it's driving, it's building up this data set internally to figure out, okay, I know what I've driven over before and it's been safe. Looking at this area, maybe the rover driver told me to go from point A to point B, because from what they could see in the images, it looked like it was safe, but I can see as I'm driving, oh, I hit this point, this area is not safe. I need to make the decision to go around it. Right now, that's a pretty manual process. You get the images back from the rover engineers here on Earth and the science team look at those images and try to guess as best as they can, well, we think this is the safest route. But they're not there on Mars, and it's hard to figure things out from images remotely. So the more that we can have the rover do on its own to make these decisions, the faster the operations can be on Earth. Hopefully the less dangerous it can be, because the rover is smart enough to make some of these decisions. And so we're decreasing the operational timeline and also increasing the science efficiency and science return, because you're also sending less data back to Earth that is being used for decision making in terms of the navigation and the operations. So you freed up that limited part of the bandwidth to send data back for science. So if we turn off that layer and go back to just what the lovely Mars yard looks like on its own. So this is what it looks like by itself, and we can drive the rover around this way as well. And so they've tried to add a bunch of different little hazards in this Mars yard that you might want to drive around. So right there at the very farthest part in the distance, that's the steepest slope that you can drive up in the Mars yard to try and test that part out. That black pile of stuff right there is sort of the loose sandy demo area to see if you can drive that without getting stuck. You can see the little lights coming on and off on the front of the rover as I start driving and stopping. So it's pretty cool. And MCSS has a program called Mission Control Academy where they're actually having students come in and learn how to do this type of rover operation. So they get to drive these rovers and play around with them with the Canadian Space Agency Mars Yard as well. So we're going to switch back again. So that's a little bit of a preview of some of the stuff that we're looking forward to on the software side, but we have a lot of innovation that's happening on the hardware side as well. So what kind of technology are we looking at for the next Mars rover and a little bit beyond that? So the Mars 2020 rover looks a lot like Curiosity. It's basically, like I said before, Curiosity 2.0. A lot of the instrumentation is very similar, but just upgraded because it's the future. Some of it is not all that advanced. Again, the science cameras are still 2 megapixels because we're using heritage from the cameras that were de-scoped from the earlier Curiosity rover. But we do have some souped up stuff like the wheels that will hopefully be better now that they're titanium instead of aluminum. We have a few different science instruments, and this rover is going to collect tiny core samples and put them basically in a lunchbox that it leaves on the surface of Mars somewhere. And then we're going to send another mission to go and collect that lunchbox and bring it back to Earth so we can analyze those samples in labs here to try to answer the question, was there ever ancient life on Mars? And we're specifically looking for ancient life with this rover because there are a lot of rules around things called planetary protection that make it really difficult for us to go to places in the solar system where there might actually be life today. It's kind of a conundrum because if you're trying to search for life, you think you'd want to go to the places where there would most likely be life today. But we also don't want to contaminate those places with bugs that we bring from Earth. And it's really, really hard to sterilize stuff, even with the harsh radiation environment of space and the vacuum and the temperatures. Stuff still survives out there. So there are bacteria on Mars right now on the outside of a lot of these missions. They're just dormant because they can't survive the trip or they can't metabolize once they get there. But the coolest part of this mission, well, 2 cool things. One of them is that we're using a slightly new landing technique. So we're still using the sky crane, but now we have something called terrain relative navigation. And so the rover is taking photos as it's descending, again, like it did with the descent imager before, but it's taking those images, comparing them on the fly to an orbital map of hazards that's been made by an engineer here on Earth. And then if it looks like it's coming down on top of something hazardous, it can divert itself if it needs to and then land somewhere else. Because even though we know generally where we're landing on Mars, our landing ellipses, as we call them, are still pretty large. Sometimes they're like 100 kilometers across. So we know the general area, and we're going to land somewhere in that ellipse unless something goes awry. So having something like this to make sure we don't accidentally land on top of, say, a pointy boulder is really helpful. And maybe the coolest piece of technology that's on this is, well, all of the video keep talking with overly dramatic music. Demo at JPL to show that this thing can fly in the Martian atmosphere, which is significantly thinner than Earth's, less than 1% of Earth's atmosphere. It's basically the equivalent of being at 10,000 feet in elevation here on Earth. That's the type of atmosphere we're trying to deal with flying on Mars. And people weren't sure if you could make a helicopter that would fly in air that thin. So we have trouble flying, regular helicopters at high altitude here on Earth. So this had to be completely redesigned for this new atmosphere that we're dealing with. So this is flying on the Mars 2020 rover as a technology demonstration because we've never done this before. And so NASA doesn't like to throw a lot of science instrumentation on something that it doesn't know if it's going to work or not, because why spend all that money if it goes there and there's a high chance that it will fail? So we're using this to fly ahead of the rover, and ideally on future missions, it's going to be taking images like you saw in the video that the rover can then use to do some of this terrain navigation, like automated planning, and also be used by the engineers on Earth to try to do some of that navigational planning as well. So instead of relying on images from orbit, which at the highest resolution for Mars are 25 centimeters per pixel, so we can resolve things that are 75 centimeters in size. That sounds really good, and it is, but it's not quite enough to resolve things like small boulders that might be a problem, or small sandy patches that could pose a hazard for the rover. So this thing will help us, again, greatly reduce the operational timeline to figure out how we're gonna drive and what the safe routes are. This thing autonomously takes off and lands, and the only instrument on board right now is a GoPro-like imager to take those pictures. In order to deal with the atmosphere on Mars, it has these coaxial rotors that spin at 3,000 RPM, which is about 10 times faster than a helicopter on Earth. It's solar powered, but again, all of that motion takes a lot of power, so it only can operate for about 2 to 3 minutes a day. And it's planned to last for 30 days. But basically the goal is to show that their thing can take off the rover, fly a little bit, land somewhere far away that is not crashing on top of the rover, and they will call that a success. Then if that works, hopefully on future missions we can send some with more instrumentation to do a little bit more. The goal is that it will hopefully do 4 of those flights and fly up to 1/3 of a mile away from the rover. But we're not just looking at drones for Mars, we're also looking at helicopter drone type things for Titan. You need an atmosphere to do this, obviously, and Titan is a moon of Saturn that has a really thick atmosphere that is a lot like primordial Earth. It's also the only place in the solar system where we've seen what look like lakes of liquid. But instead of liquid water, they're actually liquid hydrocarbons, so kind of like gasoline. And we want to take a look at them because, again, a lot of goo on early Earth was like that, and we think that's where life might have started. So we want to go and take a look at Titan and figure out what's going on. The Europeans did land a little tiny lander on Titan 20 years ago almost now, but it landed in one spot, took a few images on the way down, and that was it. So these things would be able to fly around and actually take a bunch of pictures of Titan and get us a better idea of what's going on underneath its thick atmosphere. So the call of action I want to leave all of you with is, what can you do in the box of space? I have a feeling that a lot of you in the room are not space people, like you're not working on these rovers or on these missions. I assume a lot of you are like tech programming type people, machine learning, AI, all that kind of stuff. And we could really use your talents to figure out what can we do in space in the future. With all the limitations that you've seen that we have to deal with, is there anything new that you feel like you can bring to the table to help us do space better? Can we do things more efficiently? Can we, process data better? Can we collect more data? Can we send data back better? Can we get more power? That's the biggest one. If you can invent a better battery, NASA would be really happy, so please give them a call. But basically, I want you guys to think about the box that we deal with in space, and if there's something that you might be able to do to contribute to the things that we can do within that tight parameter space. So I want to say thank you to the folks at Meteor Studio at Arizona State University who actually put together the augmented reality rover, and Ali Bahremand here in the front row who did all the work on that. If you want to do your own augmented reality tour of Curiosity and you have an iPhone, it's not available for Android yet, but you can search for Explore Curiosity in the App Store and it can come up and you can go through on a tour. There's a little audio guide and written guides you can go through and take a look at all the different pieces. And if you want to learn more about Mars, you can follow me on Twitter as @Tanya of Mars. Thanks.